Finite Math, Chapter 10, Section 1, Frequency Distributions. Researchers often want to learn the characteristics or traits of a specific population or group of people or animals or plant life. These characteristics they're interested in and that they measure are called variables. And most of the time it's very impractical or really even impossible to measure something for an entire population. So instead, researchers collect data on a subset of the entire population. It's called a sample. When an entire population is researched, that's called a census. And often a census is just, like we said, impractical. It just doesn't work. There's too much, it takes too long, and the population changes too much in that time. So most of the time what researchers are going to do is they're going to collect a small group of that population, and it's called a. Okay, a word about samples. In order to get a true picture of the population, you don't have to have a particularly large sample, but it does have to be representative of the entire population. And one common way of getting a sample is to perform what's called a simple random sampling. Now, again, it's really difficult to get a good representation here because depending on your sampling method, you may cut out a part of the population unintentionally. For example, one method people will with the internet or with some surveys is they will invite you to call in or to log in and give your opinion. Well, you're really only going to get people who really are passionate about the topic to give their opinion. If it's an internet thing, you're only going to get people that are really internet savvy, that are used to using it, which is most of us now, but it still will cut out a pretty good segment of the population. A classic example of a poorly selected sample was the poll that was made by the Literary Digest in 1936. It predicted that Alfred Landon would win the popular vote over Franklin Roosevelt. Well, in fact, Roosevelt won with 62% of the popular vote. And you may wonder, how in the world, what happened to make this so off? Ask what happened that caused them to be so far off. Well, the problem was that the Literary Digest took their sampling by using names in the phone book. Well, this all happened right during the Great Depression. So only the people that were well off had the money to be able to afford a telephone in their home. That would have been a luxury. So by taking their sample from the telephone directories, they were cutting out a huge segment of the population. They weren't being represented, and so the poll was just very off of the actual reality there. In a statistics course, if you ever take a full statistics course, you'll learn about many methods of sampling that are used in order to obtain a representative sample. So they've developed a lot of different methods over the years, and if they're followed, you stand a pretty good chance of getting a decent sample. But you do have to be very careful in order to really be able to make conclusions based on your sample. You have to really make sure you've got a good sample. So once you've got your sample and you've collected your data, you need to organize it, because the whole point of collecting data is to be able to analyze it and make conclusions. So with numeric responses, what you usually do is you group the data into intervals of equal size. For example, we have this list of the 2011-12 annual tuition in thousands of dollars for a random sample of 40 community colleges. It says identify the population and the variable, group the data into intervals, and find the frequency of each interval. Okay, well, first of all, the population. The population is the large group that the small group of samples comes from. So the sample was 40 community colleges. The population would be community colleges, presumably in the U.S. So that would be the population. The variable, well, what are they collecting data on? They're collecting data on annual tuition. So that's the variable. Now we want to group it into intervals. So what we're going to do is that we are going to group them into intervals with a size of 0.5. Since we've got numbers that are decimals here, that's probably the best way to go. Now, you're going to go from 1.0 to 1.4. If you count that on your fingers, that's 5 numbers. 1, 1.1, 1.2, 1.3, and 1.4. And then your next group will be 1.5 through 1.9. And then 2.0 to 2.4, 2.5 to 2.9, and so forth. And your last interval will be 5.0 to 5.4. And that gives us 9 equally sized intervals. The intervals do need to be an equal size. You kind of have to play with it. How do you know how big to make your intervals? It really just depends on the data. If your intervals are too big, then you really don't get a good picture of the data spread. If they're too small, then it just kind of gets pointless. Why make intervals at all if you're just going to have them so small? So you just have to play with the numbers and see what works the best. So the first thing they did is they summarized the data. They tallied the number of schools in each interval. There's our intervals, and they just kind of went down the list and marked which interval each thing belongs in. Notice that we don't have any schools in the 1.5 to 1.9 interval. We're still going to include that in our data because there'll be a gap there, but that's still important. Sometimes the gaps tell you as much as the other bits of information. This is called a grouped frequency distribution, and it's a frequency distribution because it tells us how often numbers fall into those different intervals. You could tell a lot just by looking at the frequency. We can tell that the most number of colleges, or the interval that had the largest number of colleges, was 3.5 to 3.9. Again, there's a gap between 1.4 and 2.0 where there are no colleges that fall into that. So you can tell a lot just by looking at this information. Now, when we do statistics, generally speaking, we always want to include a picture because pictures are very quick and easy to read. We want to make them clear. We want to make them labeled. So there's a lot of different ways that you can picture information, and we're going to go through many of them. Now, the downside of doing the intervals is that specific information is lost. That's why it's really important to keep your data, because you know that there were a certain number of colleges. I think there were 11 from 3.5 to 3.9, but we don't know exactly how many charged 3.9 thousand or 3.6 or whatever. The specific information is kind of lost when you have the intervals. So you do want to keep that and make sure you have that on hand too. You can display this information from the frequency distribution in a histogram. We've seen these before. There's bar graphs. It looks like this. Each interval, the x-axis is our intervals, and you go from 1.0 to 1.4, 1.5 to 1.9, and so forth. The interval size determines the width of the bars. The frequency, how many are in each interval, determines the height of the bars. And what they've done here, if you're wondering about the red line, they found the midpoint of each of the widths. So between 1.0 to 1.4, the midpoint's 1.25, and they put a dot in the middle of the bar at the top of the bar for each of them, and then they connected them with a line. And this line is called a frequency polygon. Technology tip here: you can create this the histogram and the frequency polygon in your calculator. What you want to do is you want to go to list 1, you hit stat edit, and then in list 1 you're going to list your data, and then you're going to put, and that's the raw data, not the intervals, the actual data. In list 2 you want to put the midpoint for each interval that we figured out, and then in list 3 you need to put the frequency for each interval. Okay, so those are the 3 lists you need to fill in. Then you're going to go turn on plot 1, which is second, then y equals. Select the histogram. You're going to turn it on. You're going to go to the one that looks like a bar graph. The x list should be L1 and frequency should be set at 1. Next, you're going to go ahead and turn on plot 2. You're going to select the second style in the menu. Kind of looks like it looks like a frequency polygon. For X list, you need to select L2, which you can do by hitting second and then the number 2. And the Y list should be L3. And again, you can hit second and then the number 3 to get those to come up. Then go to Zoom and select Stat 9. By the way, make sure you don't have anything in the y equals because that will kind of mess up stuff. But go to Zoom 9. And you're probably going to want to adjust your window. The X-min should match the lowest data value in your raw data. The X-max should match the highest, or at least the highest end of your interval and the lowest end of your interval for that. The X-scale should match the width of the interval. So for the list we just did, I'm going to set the X-min at 1, the X-max at, I believe it was 5.4, and then my X-scale is going to be at 0.5. And then good to go. These are some screenshots. There's my 3 lists that I set up. And this is turning plot 1 on. This is turning plot 2 on. Notice I've got the second type highlighted. X and Y lists are selected as L2 and L3. My window, I actually went to X max for 6. You could stop it at 5.4 if you want to. I like to go a little beyond that. My X scale is 0.5. Well, my Y max is 12. Your Y max needs to be at least as big as your tallest bar, which in this case was 11. It had 11 in it. I like to go a little higher. And then this is what it looks like. Now, another way to organize data is to use what's called a stem and leaf plot. And a stem and leaf plot has the advantage of it gives us a distribution, it gives us a picture, but we keep all the individual data points. To create it, you're going to take each of your digits and you're going to separate them. You're going to take each of your data items and separate them. You're going to have 2 parts. The first part is going to consist of the first 1 or 2 digits, and then that's the stem, and the remaining digit will be the leaf. You need to provide a key with it so the reader understands how to interpret it. Now I'm going to show you how it works. So here's an example of a data displayed as a stem and leaf plot. So notice the stem. The stem is all, in this case, single numbers, although it could be double, it could be 2 digits. The leaf is always single numbers. And notice at the bottom, the key tells us that 5/6, in other words, when you have a stem of 5 and a leaf of 6, that indicates 56%. Okay, notice that all of the points are displayed in numerical order. I can look at this and see the original data. Originally, we had 56%, 67%, 67%. It was in there twice, so the 7s are listed twice, and 69%. 72%, 74%, 77, 77, 78, 81, 82, 82, 83, 84, 88, 90, 92, 93, and 94. So that's all of our original data. You repeat things as often as is appropriate. You list the repeats. If you were to happen to have, let's say that there had been no numbers in the 60s, well, I would have left a space. I would have put the 6 for the stem, but I would have put nothing in there for the leaf to indicate that there's a gap there. So your stem, you want to keep it in that numerical order, even if there's nothing that's in that particular value. And there are the listed original numbers. Let's try to do this. We're going to construct a stem and leaf plot for the data from example 1. So here's our data. A great way to divide this up is to make your stem the 1's digit and make your leaf the number in the 10th spot. Why don't you pause the recording, see if you can do this, and then resume to check your answer. So here we have our stem and leaves. And what they did was they split it again by 5s now, or by 0.5. And when they do that, notice the stems are each listed twice. So the initial stem, you're going to have 1.1 through 1.4. The second one would be 1.5 through 1.9. And then you have the 2.0 through 2.4 and the 2.5 through 2.9. And it's fine to do it this way. It matches with our histogram, so that's not a problem. You split it up like this when doing it with, would just kind of make it too large. Otherwise, your leaves would just get really long. So here we go. And at the bottom, you have the key, 5/3. Now, notice they didn't put 5.3. They put what it actually means. And if you recall, all that was in thousands, so 5.3 would have meant 5,300. So that's what they're putting for their key, so you can actually read it. Notice we leave the gap for part 1. And there we have it. Okay, here we're going to go the opposite way. We're going to list the original data from the stem and leaf plot. So pause the recording, give it a try, and resume to check your answer. Okay, here's all the data. And by the way, when you look at a stem and leaf plot, one advantage, like we said, is it does let you see all the original numbers. Another advantage is it still gives you an idea of the shape. You can still see which interval had the longest or the most number of entries. You can see gaps and things like that. So it has the advantage of giving you an idea of shape, yet at the same time retaining all the original data. Like I just said, histograms and stem and leaf plots help us assess the shape of a distribution. Now we're going to talk about the basic shapes. One common shape is called uniform. This refers to where all the bars are about the same height. This would be an example of uniform. Notice they're not all identical, but they're really close. I mean, there's not a lot of change here. So it doesn't have to be perfectly the same, but very close. Another shape is the classic bell shape or bell curve. It looks something like this. It peaks in the middle. It tapers off pretty equally on either side. It's pretty symmetric. Again, statistics is a real-world math, and the real world is messy, which means that you are rarely, if ever, going to get data that falls into a perfect symmetrical shape. So you're looking for close, but not necessarily perfect. This would be considered close, and it would be considered a bell-shaped or a normal distribution. Now, if it's not uniform and it's not normal, it is skewed, and it can be skewed in one of two directions. The distribution is skewed to the left when the long tail is on the left, as in the top diagram here. You'll notice that the bulk of the height is all on the right, and then as you go further to the left, it just tapers off into this kind of like a tail. And it is skewed towards the tail. It is skewed towards the direction the tail is going. So the top one is skewed to the left, while the bottom frequency distribution is skewed to the right, because you see the bulk of the height is all in the left and the tail tapers off to the right. So try this. Characterize the shapes of these distributions. Pause the recording as you do each one. You shouldn't need long, and then resume to check your answer. Again, remember, we're looking for close but not perfect. So try this first one. Okay, this one is considered normal. Now you may be thinking, well, you got some, kind of irregularities there, and you do, but for the most part, it fits the profile of a normal curve. And again, we're looking for close, not perfect. This one. Okay, this distribution is skewed to the right because the tail is to the right. The bulk of the height is all on the left, and it drags off to the right as the tail. All right, the rest of these are extra practice, so go through these, pause the recording as you try them, and resume to check your answer.